knowledge, but also what is behind and all important changes we observed during the last decades. And to do this, of course, we have some very nice invited people to this job, and this afternoon we have really the pleasure to tell us something about the solid earth, which is solid but very dynamic, and it will be Cynthia Ellinger, our guest. So, in a few words, Cynthia, she's here. She came from very far away, University of Rochester. I hope you are in longer Vienna time now. Lots of projects on her side, mainly with magmatic modification of continental and oceanic lithosphere, and also magma and volatiles in early stage drifting. She was a former position in Leeds University and Royal University of London, and lots of hobbies, archaeology. I think you are not very happy with archaeology in Vienna, but who knows, if you can find something nearby. But hiking may be a solution for your spare time if you have any. And also music here in Vienna. I hope you enjoy stuff. So, it's a huge problem because I had one extra slide you sent me this morning. I'm very sorry. And it was really the slide showing a few important questions you are going to address, but because I'm not in your field and you are so good, I'm really going to give you the floor, and please bring us to our solid earth. Thank you.
Thank you very much.
So my slide is lost and your password is important. Okay.
Well, thank you. It's a pleasure to speak, although it's with trepidation I prepared for this. My graduate student pointed out to me when we were joking last weekend that my talk was not 20 minutes. It was an hour and a half, or the time allocated to it, which was better than I knew then than on the airplane on the way over. But what I'm hoping to say to you, I love what I do, and I hope I can convey then a sense of awe at the processes occurring in Earth. And I don't pretend to be an expert in many of the areas that I'm going to be talking about, but I hope that I can try to make linkages between the core mantle boundary and our surface, fluxes, and changes in the planet that will pique your interest and provoke perhaps some new connections and new ways of approaching problems. So that's my objective. For those of you who know me well, you will see that I've already placed myself in some hot water. But I may continue to do so as the talk proceeds. So let me just see whether I can figure out how to do this and still dance around the room. Can we talk these two?
Cynthia,
yeah.
Maybe we can stay there.
Yeah, you can use that one.
I can use this one.
Yeah.
Okay. All right.
Yeah, better.
That's not going to be good. So how can I do it?
Microphone, please, for the streaming.
But I can go forward and backwards with these, yeah?
Yeah, you have also here now.
Yeah. A mouse. Earth is unique, as we know. It's not just because we're here, but because the planet itself is habitable, and we have a regular flux from Earth's mantle to produce the atmosphere and maintain the atmosphere that we have to have this hydrosphere on the planet. And this constant flux of magma, volatiles, and heat transfer maintains our environment. But I think in the diagram below from NASA, just in showing then a tomographic model of Earth's mantle and the core, the inner core, the solid inner core, the outer core, and the dynamic mantle rising up to beneath the plates and then changing Earth's surface over time. It's that flux then and that the plate tectonics that in part makes this planet habitable. And so it's an important part of the system and in the way that we approach planetary exploration as well. Whoops, that's not it. Okay. Apologies. Oh. Aha.
Switch.
Okay, this is much better. Apologies. I'll get there. Whoops. Okay. This is a diagram that Rajdas Gupta and Hirschman put together showing the fluxes of carbon and from Earth's core to the surface and within the mantle. And this is available information at the time they wrote this paper in 2010. There's quite a lot of information on here. The top diagram, whoops, is, I'm trying to figure out how to use the pointer. There it is. Whoops, it's a bit weak. Okay. Here are some of the sources then. These are the plausible carbonate melting zones. They may or may not be connected or linked to one another depending on the oxidation state of the mantle. But so we're looking here then plumes, mantle plumes may rise up and bring new material to ocean islands or flood basalt provinces. And those of you who went to Jason Morgan's talk will have seen, heard a nice exposition of how important this is to the asthenosphere. Subduction zones then recycle material. But one of the things that you'll notice on this diagram, and if you look at the fluxes down below as well, continental rifts are not there. A flood basalt province isn't really there. We have ocean islands, and we have mid-ocean ridges, ocean islands, and volcanic arcs. And in every textbook, and those of you who teach undergraduate and graduate students, you know that we teach them that continental crust is produced by island arc magmatism over time, although there's many other articles pointing out that the lower crust in island arcs isn't what we have in continents as well. And so there must be differences and the chemical budget isn't all worked out. So there's room for consideration. And as the talk goes on, I'm going to present some numbers then for a continental rift system that should be added to this diagram. And I'll also talk about CO2 fluxes and water fluxing as well. This is a diagram prepared by Parai and Mukhopadhyay, and I'm sorry for butchering the last name. But this is just a recent paper looking at the global water budget. And if we look then that we have water fluxing out from ocean island basalt again, from mid-ocean ridges, no continental rifts, back arc spreading, and arc volcanism, oh, continental rifts. Is there magmatism in continental rifts? I think when preceding, or as you'll see, I'll try to present background information then that will address that emission as well. But in this system, the fracture pattern, fault patterns on the sea floor, particularly those associated with bending, enable more fluids then to enter the oceanic upper crust and be brought down. And then, of course, the sediments and the sediment flux into this trench system then is going to contribute back to the water cycle then that we're seeing in here. Okay, but as I move along through the talk, later on, I'll present some information then, some recent work from studies of passive margins, the Iberian margin with this extensive 3D data set with also the extent of crust and upper mantle velocity control that shows large volumes of water entering and serpentinizing the uppermost mantle during the late stages of continental rifting. That is an important part of the that could have important implications then for plate tectonics, particularly the onset of collision. So let me preview. I work on continental rifts. I am rather embedded in the continental rift community, and I like to start the talk with something I'm comfortable with here too, and looking at fluxes. And so if we look, and I've isolated the upper part of the plate, we're going to start from the core mantle and work our way up, but I wanted to introduce some information about continental rifting processes. So that in the continental rift zone, we have heat transfer to the lithosphere through the process of replacing stretched mantle lithosphere with hot asthenosphere that's passively upwelling to fill that space. As it passively upwells, it will be susceptible to adiabatic decompression melting. If there are volatiles within that melt, and depending on the temperature, if there's a thermal anomaly, like a mantle plume, or an edge effect, then there also may be the enrichments, or if the mantle lithosphere itself had been enriched by previous subduction episodes, then we may be releasing volatiles, and they would then be finding pathways up to the surface as well. The upper crust, it may be faulted, and we may have zones of magma intrusion. And these compositional boundaries then serve as barriers, particularly the one at the crust-mantle boundary, where buoyant magma then reaches, there's basically the same density as the surrounding material or surrounding crust, and so it's no longer buoyant, and it may be stuck then or underplated to the base of the crust until it can find pathways then to the surface, and where it may reside in a crustal magma chamber or may be intruded as a dike system. Now, in this, I'm not going to spend very much time here on this. Later on, we'll talk about rheology and the importance of these processes, but I just wanted to highlight here that in many ways, we go to conferences and there are groups of people that are working on active deformation, so earthquakes, volcano deformation, and then there are groups that are looking at time average deformation patterns from either seismic reflection or refraction or other types of studies. And maybe, perhaps not as often as we should, we intersect with those two communities. And so in some ways, what I'm trying to do is put together more of a time average deformation with the active process itself. So earthquakes are stress buildup over time periods of hundreds of years, perhaps to thousands of years for continental interiors with low extension rates or compression, whatever, plate boundary deformation rates. But then the strain is released, or the stored stresses are released very rapidly over periods of seconds, or unfortunately, in the case of our colleagues in Ecuador who suffered a magnitude 7.8 earthquake over the weekend, they may be minutes and with lots of large damage. So earthquakes themselves then are very short period events, whereas the stress buildup cycle is much larger. And also the isostatic response to these changes is also on a much larger time frame here. The hydrographic cycle and others are longer than many of these, but they integrate then and over time averaging then produces these types of patterns that we see here. And the way that the lithosphere then responds to that is going to be also time dependent. So how rapidly it's stressed then is going to change then the way that it responds. And obviously, at our surface, we have abundant evidence for the dynamism of process. And INSAR, GPS, and global and local seismic arrays are providing a near global picture. Obviously, the seafloor is not as well examined, but with, I heard a talk recently, I don't think the paper's out yet, but Laura Wallace and others were actually able to, with digital pressure gauges on seismometers on the seafloor off the Hikurangi margin in New Zealand, were able to capture a slow slip event that they'd predicted from onshore patterns with these digital pressure gauges and better constrain than the slip along a subduction margin to try to better understand. So, you know, equally then we're hoping that we're going to be able to better examine processes across the globe. But with INSAR and integrated with GPS, INSAR gives us the spatial resolution, GPS gives us the temporal resolution. We're able to then look at time variations and deformation. So in this case, this is an interferogram from the Afar Depression. This is about a 60-kilometer long length that ruptured in a large dike intrusion in 2005. But this is the post-diking deformation in terms in the interferogram with the post-diking aftershocks to this that may have involved some additional magma intrusion. This is an inflation and a reinflation of these two magma chambers immediately after. This is a subsidence pattern, and this is was an uplift pattern in this area as well. On the right-hand side, you'll see this is a Derek Keir, who's about 2 meters high for scale, but this is a surface fault break from a magnitude well, at one of a swarm of earthquakes, the largest of which was a 5.4. And in global relations of earthquake fault slip dimensions, this should be on the order of 0.5 meter of displacement rather than more. Okay, so sorry, the black is the pre-existing fault zone, and this is the rupture from the earthquake. But this would, by examining this fault scarp, we might expect that this had ruptured in a magnitude 7 or more earthquake. So this is a fault that formed above a dike intrusion. So this example is as much saying that we're learning a great deal, or we're still experiencing new phenomena that change the way that we quantify plate tectonic processes. So what I'm going to try to do is talk about the transfer of fluids, magma and volatiles from the lower mantle to the surface. And it's driven by compositional as well as thermal buoyancy. Global data sets enable estimates of the magma and gas fluxes to the surface. And these fluxes then are going to modulate our horizontal and vertical rates of processes as well. And then in terms of strain localization and initiation of shear zones are obviously a fundamental component of plate tectonics. We have to be able to have separate plates that move, and so our processes then, any fundamental process then has to explain how this happens. And I'll point out one of the major questions in plate tectonics that remaining is how cratonic lithosphere, cold, thick, strong cratonic lithosphere can actually, how fault systems and strain localizations can develop when the forces available are less the integrated strength of the plate. And so throughout the talk too, wherever possible, I try to feature exciting new work by early career scientists. Now, French and Romanowitz published this compilation in just last year, a new global model of mantle tomography and their implications then of plumes in the lower mantle. So this is a slice then, or it's a perspective of the globe at 2,800 kilometers depth with the red zones, areas of low, much lower velocity. And here's a scale over here. This is the normalized shear wave velocity that's about 2% and plus 2% into the deepest blues. And with these circles then highlighting areas that are identified then as plumes, and with some quality control as primary plumes, somewhat resolved and not associated with any hotspot at the surface. So hot zones, but not associated. And it's this area here that I'll spend some time talking about, because I think there's a great deal still to what we can begin to quantify quite a lot of this information about flux from studies, compilation of studies over the past couple of decades in East Africa, a really exciting array of experiments that have enabled us to look at continental tectonics in a new way. So one of the, so this is a recent paper by Thompson et al. In G-cubed, where they're looking at using receiver functions, so seismic methods, and these are ways of taking upcoming rays that are converted from a P to an S or an S to P, or within Earth's mantle at velocity discontinuities, and they help us find then compositional variations within Earth's mantle. And on this side, we can see pierce points, or these are where the rays are then coming up. And so this is the zone then that's being sampled by seismic waves. And this is giving us information then about the structure of Earth's mantle, obviously. We have petrological studies and geochemical studies that provide point information, and these are then complementary to them. But in terms of, I hope everyone here can see roughly the stacked reflections here, they're stacked on top of velocity anomaly information as well. Here's the 670 discontinuity, the 410 discontinuity, and this negative velocity zone is interpreted as the stable melt layer. There's a discontinuity at 520, and these low velocities in this area that Thompson and others, and an earlier study by Nyblade and Julia, also suggests that this is evidence for hydrous upwelling from the core mantle boundary. And it's moving up then through the mantle transition zone and coming up towards the base of the plate in these areas. And I think it's important because it's quite important to consider the role of water. And if these are zones where, or these patterns are telling us then about rising water, then as we move up to the asthenosphere, we'll see that a hydrated asthenosphere is going to have a strong importance on plate tectonic processes. So these are, again, this is work of quite a large group of scientists here. Well, the lithosphere, asthenosphere boundary, or the base of the plate, is a low viscosity zone. It's low friction. It enables the movement of the plates without over our surface and over the mantle. There's coupling between the two, but obviously it's not strong because we wouldn't be measuring the plate velocities that we see on Earth if that were the case. So yes, we have some coupling, but a lot of that coupling has to do with fluxes of magma and volatiles up through the plates as well. We can obviously transfer stresses through that boundary, but this low viscosity zone then and the role of fluids is really important, and it's highly debated. And I can't, I'm not going to offer new insights in this. I'm just providing some additional information to help understand the system. And in this case, Sakamati et al. Looked at a series, they generated a number of models of the mantle where looked at the rise then of melt within, small amounts of melt, and where it would accumulate, so where melt is retained within. And magma mobility then, or they found that there was kind of a sweet spot for magma mobility, and that's at the base of the lithosphere, asthenosphere boundary. Now in this case it was parameterized more for oceanic lithosphere, but I think my point here is just that it's not, we as a community have got to a point where we can parameterize and physical models that can help us understand the migration and percolation of melt through the mantle up to the lithosphere, asthenosphere boundary, where we then start to have much higher resolution studies, and we can start to then link these fluxes from deep to the processes of greatest societal relevance, volcanoes, earthquakes, and others that then are going to shape hazard development and our energy, renewable energy systems as well. So move ahead. And when we get to the lithosphere, asthenosphere boundary, cratonic roots and induce and deflect the mantle flow, and these enhanced vertical velocity induces melt generation. So those geologists in the room who've worked in continental regions are well aware that cratonic or Archean lithosphere in many places is unusual. It may have a more buoyant mantle. It's chemically distinct. Lavas erupted through Archean mantle are quite different. And these deep roots then serve as keels or to slow the plate in its movement over the asthenosphere, but also too to deflect the mantle flow around the deep keels. So here are just two sketches. This is Scott King's model. There's several variations of this, but in this case, there's an edge at a cratonic keel. So imagine this gray zone as the lithosphere. This is a thick, deeply rooted Archean craton, and mantle flow is impinging on the edge of that, and you see the flow patterns in small-scale convection. And then we can also then generate, or in this area, then you would generate some melt along the edges. Now these are papers from the last century. I've always wanted to be able to say that, but it's ancient work here. This is a very crude sketch of lithospheric thickness based on what we knew at the time. Isn't it great how much we've learned since this time about lithospheric thickness? I'll show you a new diagram prepared by Stuart Fishwick in a second. But at that point in time, here are the thin zones from the Mesozoic rift system that affected a very large part of the African plate. The East African rift is not unusual in the extent of the deformation. So these thin zones would have existed at about 40 million years ago when the first lavas erupted on the surface in East Africa associated with the present day situation. And this is just showing how these deep roots then would deflect flow from a large plume centered beneath here and shoot the melt in different areas. And as kind of as an aside, when Norm and I did I was on sabbatical at Stanford, and we ran these models, and our sole intent was just to see how far away from the plume center hot asthenosphere susceptible, or plume material susceptible to melting could go, how far away from the plume center when it rose beneath a relatively realistic lithosphere. And this is the prediction then of the melt generated as well. This would be melt volumes. These would be the largest accumulations. And these pre-existing thin zones would help serve to guide or pawn that material. But we didn't intend it to be a model to explain East Africa, and we were pleasantly surprised that it was reasonably good fit. So anyway, moving along, folks are coming up with better models, looking at these interactions and coming up with new ideas. But I just wanted to point out that as we build these new databases to really accurately constrain the lithospheric thickness, it is a critical problem, as well as the role of fluids, or the amount of fluids in that lithosphere-asthenosphere zone. I just very briefly, because this is work of others, I participated in this work, but what I'm showing here is anisotropy patterns. So seismic waves that pass through an anisotropic material like olivine, or if we have areas with olivine that's aligned in a direction with mantle flow, or aligned fracture patterns, or melt-filled fracture patterns, then we can have some splitting of the S waves, and so there'll be a fast and a slow direction. We can measure both the amount of time between the two, the amount of splitting time between the fast and the slow wave, and its direction. And so that's what's shown, that's what's shown on here. And in this case, if we expected, it's very important, this is the plate motion vector for Africa. So if you expect to see a shear associated with decoupling of the plate over the asthenosphere, it should be going in that direction. And roughly, if there were a strong strain fabric associated with stretching of the lithosphere, that strong strain fabric should be in this orientation. And instead, we see rift parallel associated with rising melt and fluid-filled cracks beneath the plate, and with the strongest amount of splitting at the edges of the rift zone. And this is now a compilation of even more areas in East Africa, and we see strong along axis orientation, indicating that, or interpreted as aligned melt-filled fractures that are transporting magma into the plate and modifying its structure in a fundamental way. And there's a parallelism in the crustal splitting patterns that are associated then with magma intrusion zones, all these red zones. So here we are in, I should introduce, here we are at the Horn of Africa. This is the Red Sea, the Gulf of Aden, the Gulf of Tajura then comes in through here. This is the southern Red Sea Rift, and the East African Rift starts here and continues down into East Africa with the Eastern Rift and the Western Rift here. There's quite a lot of new information with SKS splitting. There are about 80 more stations and analyses that we could be adding, and so there'd be a lot of new results in future to be better constraining the flow. But what's important here, I think, is that this rift parallel pattern is very typical of areas with strong amounts of magma, and the interpretation is that we have melt rising up through the plate, and with the most enhanced splitting at the edges where we have steep velocity gradients. Here's a mantle tomography diagram, and at this point, I don't want to spend a lot of time on this. This is from Hammond, the tomography is from Hammond and Ian Bastow, who's here in the room. It's many different experiments and a lot of data that have gone into this. But in this diagram, what we're imaging at about 75 kilometers is the base, near the base of the lithosphere. So the rift zone is here. Here's the Red Sea rift zone. These greenish patches then are where we have surface magmatism. These are the long lines of eruptive centers at the surface. These are the cold zones along the edges, so there's still thicker lithosphere, and hot upwelling zones in many of these areas. But what we wanted to see, or Kate Reichert wanted to analyze then the S to P receiver functions to see what the lithosphere was like above a plume province. In this diagram on the right-hand side, the blue is areas where there's a contrast or velocity step at the base of the lithosphere, and the pink is where there isn't. And I'll show you in a second what the contrast is. So in the interpretation here, this is where the base of the lithosphere can be imaged, and here's where it's basically been removed, and the base of the lithosphere really is undefined, and it's more a melt horizon. So what, in this case then, these are comparing, this would be a typical change then, this would be the conversion in the lithosphere's asthenosphere boundary in this lower velocity layer at the base of the plate. This is typical of continental regions, and so this would be where we call the base of the plate. It's also where we'd expect then to have accumulations of melt rising up. Into the rift zone, though, we see an opposite contrast that's interpreted as the onset of melting within the zone. Now, the details of this and this in placing, this is a model imposed on the FR, and I didn't want to talk, I wouldn't concentrate so much on this, on this hot zone inside. It's a bit contentious, and there are some assumptions made, but the important part here, based on observations, we can see the base of the lithosphere, and we really don't have an asthenosphere at this point. We have a melt generation zone that's supplying magma to the surface in the FR. Okay, so we can see in a well-advanced rift system here, rifting has been progressing to a state over the past 30 million years or so since rifting started, where we have incipient seafloor spreading, and in many cases then we're starting to generate melt and have a very localized strain. But what I want to do is change a bit and look at the onset of rifting and the insights that we can gain here. So I'm going to shift gear and move to a less advanced part of the East African rift and look to see how it informs global process. So as I said before, one of the dilemmas in paradigms in plate tectonics is there's an available forces from slab pull and ridge push that's not sufficient to initiate rifting in cratonic lithosphere. So if it's cold, thick, and strong, the strength of the lithosphere is considerably greater than the forces available, and yet rifting initiates in cratonic lithosphere. So one of the early ideas for this was proposed by Roger Buck, where the additional buoyancy of magma would rise through the plate, and it would rise. So here, this is the density of the crust, the density of the mantle. This is melt. It's much less dense. It would add to the tectonic force. And on this side, it's just comparing, either on this side, this is the strength. So here in Byerly's law is defining the strength of the lithosphere. Here's the crust. There's the mantle. And this is the strength that would have to be, or the force required to initiate faulting in strong, cold lithosphere, whereas this is what's required to initiate diking in the lithosphere. So it's about 1/10 the force required. So where there's melt available, and it's buoyant, it can penetrate into the base of the lithosphere or towards the base of the crust. As it rises up through the crust there, then it's at the same density. And so other forces then are going to have to be available, or will have potentially the heat transfer then will enable the weakening of the crust to enable faulting to reach to the surface. But this diagram over here is just comparing the forces required to initiate rifting. Basically here, these are the forces required. If the lithosphere is 100 kilometers thick, as it is in cratonic lithosphere, it's even greater. The forces are much greater than the plate, the available, whereas here where magma is available. So that's one component of it, but even so, with 100 kilometer thick lithosphere, there's still a deficit. And the role of the volatiles then has never been considered, and it's still not, as I'll show you, it's not yet incorporated into rheology, but it provokes some new discussion and new analyses. So this is where I get into a bit more of the speculative part. So just summarizing then, that topography at the LAB controls the lithosphere-asthenosphere boundary, controls adiabatic decompression melting and the melt ponding. But how does the ponding and percolation through the plates influence the plate rheology? What is the role of lateral heterogeneities in these strain localization, and the role of magma and volatiles in the fault zone rheology? And the last one I don't have an answer to. It's more, these are the new observations and trying to provoke some new experimental work as well. Many folks, again, folks who teach, we explain to our students the difference between the normal stress and the shear stress, and outline then in this diagram for rocks in compression or in extension, rocks in, and rift zones are great places to do rheology experiments because rocks are weak in extension, so you can get deformation at a much lower force and get a lot of information quickly, or more quickly, potentially. But what's important here is to realize that the strength then of the materials then is going to be reduced, or these envelopes, so the strength is the area under the curve. Dry materials are stronger than wet materials. So here's a wet rock, and this is under pressurized rocks, and these are just showing some different strain rates. But let me move on. Many folks here may have known Yevgeny Borov, who unfortunately passed away far too early last October. This is work from, these are diagrams from a paper of his, a review paper in 2011. But I think what I wanted to show, as much as explaining here, this is a differential stress again. This is assuming a heat flux of 60 milliwatts per meter squared, which is pretty appropriate for a rift zone. I mean, once it's initiated. For a cratonic lithosphere, it should be maybe 40 milliwatts per meter squared. This is olivine, whether it's wet or dry. You can see then whether the large differences in the strength, what the composition of the lower crust is, and whether the quartz is wet or dry, or depending on what kind of quartz you use. What's important in this diagram, and this is for 100 kilometer thick lithosphere and 200 kilometer thick lithosphere, and this is a typical geothermal gradient superposed on top. That's a huge amount of information that's required to explain any piece of ground. So if I want to predict the deformation behavior, I need to know all of this to then put into my model so that I can use a rheologically sensible model of the plates. And what's really important to see is the huge reduction in strength then between a dry or a wet rheology. So whether or not they're volatile, or sorry, whether they're fluids in the rocks will make a very large difference in the deformation behavior. So at this point, and not knowing what the composition of the lower crust is in continental areas has been a big drawback, but as we're getting more and more information, then hopefully we can move ahead. But one other thing, when we get to fault zones, those fluids then can also cause a massive reduction in the strength of the materials as well within fault zones. And so these are studies. This is just one study that I've taken Niemeyer and Spears, and looking at fault zone processes with plastic flow, friction or slip, pressure solution, and others, and just in saying that fault zones then will also have their own rheology that needs to be constrained. So let's look at, let me just quickly then take some observations then from East Africa and try to see how we can begin to approach these major problems in understanding the rheology of the plates and the rheology of the fault zones. The East African Rift comes from the Red Sea. Here's the Gulf of Aden. There's the Afar Triple Junction Zone that Carolina Pagli this morning discussed the kinematics in this area. As we move down through, the East African Rift, we come down through here. This part of the rift, the Red Sea started about 30 million years ago, Gulf of Aden a bit earlier, seafloor spreading as initiated throughout the Gulf of Aden and only in some areas of the Red Sea about 4 million years ago. Seafloor spreading, incipient seafloor spreading here, and then relatively small amounts of stretching, less than beta factors of 2, and even less than that as we come here. This zone in through here, the topographic depression, was created by the Mesozoic rifting. And so this area, the depression, in fact, this area here was below sea level in Miocene time. There are Miocene dolphin fossils in the flanks of the present day rift. So it actually has uplifted. But these are the Mesozoic rift systems you can see in blue. You can see some down here, quite a lot in through here. And all of this area of Eastern Africa then was extended during Mesozoic time, as was this large part of the interior. So I'm going to focus on areas away from those complications, and we're going to look just at some information from here. But first, let me just Stuart Fishwick and Ian Bastow wrote a compilation paper, and Stuart took tomographic images and converted them to thickness, lithospheric thickness. And so this is a diagram. The extra contours are free air anomalies, and the blues and reds are showing lithospheric thickness. Very thick lithosphere beneath the Congo craton, the Bangweulu block down here, the Zimbabwe craton, and the Kapval craton as we move down through here. The Tanzania craton is a bit thick, but not so well resolved, the West African craton. And then much thinner zones beneath these areas as we move down of extensive magmatism, and then thickening lithosphere and through here. Okay, so plenty of opportunities as well for interactions with cratonic lithosphere. And it's important to note, as many have said already, that the edges of the craton then are where we have our generating melt. Now, one other point that I just wanted to say, so I showed you a map earlier. These are the largest fault system within the area, and it's largely the seismogenic zone. But then when we take compilations and bin information from reliable catalogs, this is the NAIC catalog from 1976 to present, and just sum up the energy, the seismic moment release, and so all these red dots are a magnitude 6 or greater. What I hope that you see is that we have localized strain in the Ethiopian rift, and this part of the rift is largely, there's not a lot of seismic energy release, but there are a lot of volcanoes. Then we lose the volcanoes and we see seismic energy release. But this is the deeply rooted Archean craton. This is the deeply rooted craton as well, and yet we have seismic moment release in a rift zone penetrating down through this area as well. And so distributed strain in terms of seismic strain across a very large area. And many of the petrologic studies and others in complement and xenolith studies are showing us that wherever the xenoliths are extruded or where we have information, we're seeing that the mantle itself is metasomatized. So there have been fluids introduced to them, and those fluids then will reduce the strength of the materials. So we're learning and seeing, so thick lithosphere at the edge of the craton, Lebat volcano in eastern Tanzania here, and these are just some petrological information. But the rocks themselves are hydrated. All right, so about this point in the talk, I figured you probably wanted to see some pictures. So here's a friendly giraffe who is obstructing the view of a beautiful 1 million year old, or beautiful fault zone that cuts nearly flat-lying 1 million year old lavas, right? Okay, so now back to some tectonics. In this case, though, Koptov et al. Looked at in an important paper, put in or made an attempt at looking at rheologically layered lithosphere. So this is a rheologically layered crust, compositionally distinct, normal lithosphere, a buoyant Archean craton deeply rooted on this side, and allowed a mantle plume then to interact with the edge of the craton, showing, and what this is showing then, this is about 20 million years after rift onset, and with the development of a rift zone on one side, entrainment of a material, and the prediction from this would be that there'd be great heterogeneity then in the eruptive products at the surface. But this plume then is going to be hydrating and bringing materials up to the surface. And so in this way, though, I think it's important that this is a fully coupled model with the lithosphere and the mantle dynamics. So now quickly then, I'll just provide some, as I wrap up, some information then from field studies. This is a delightful project, was a delightful project for me to participate in. I worked with geochemists and structural geologists from the US, from France, from Tanzania, from Kenya, many of whom are in the room. These purple are gas sampling from hot springs and soil, and a recent paper by Hugh Lee, James Muirhead, Toby Fisher. These are just the deep earthquakes within the data set. So these are focal mechanisms of earthquakes at depths greater than 15 kilometers. So even though we have young volcanoes, Oldoño Lengai volcanoes here, this is Ngoro crater, highlands, this is the fold escarpment with the giraffe I showed you a few minutes ago. These are teleseisms in blue. These are local earthquakes detected on the Crafty Colibri array. It's showing strain transfer from a border fault. across the volcanoes, and this is a shield volcano in the center of the rift connecting to intrusive zones along the length of the rift here. What I want to show you is an important part of this. What was, the depth distribution of the earthquake. So even though we have volcanoes here, 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 this one is the old Donia Langai. Okay, forget this one for the time being. I won't have time probably to talk about that. But in our seismogenic, the seismic array, we detected earthquakes then into the lower crust. The difference between these are all the earthquakes in blue, and in the white, they're just showing those relocated with a 3D velocity model from a joint inversion of ambient noise tomography, and PNS arrival time plus an additional constraint from gravity. And this is Steve Raker's work. But these are showing there's no systematic shift. It's just a different number of earthquakes. This is the distribution of these are where the teleseism occurred. But what's important is that these are in the lower crust. And so in this area of magma intrusion and magmatism, we are still getting earthquakes in the lower crust, and they have normal faulting mechanisms as well. So what and how is this process occurring? I'll just give you whoops, I'm going back here. Just very quickly, the Tanganyika Rift has even deeper earthquakes and even more of them in teleseisms in a different experiment. And I'd be happy to talk to people about that one as well afterward. But here's a cross-section then through the rift. This is a bit unusual in that with rift rearrangements in many large fault systems, this was probably the early fault system about 3.5 million years ago. Olduvai Gorge lies a bit out of the plane of this section. This is the relatively new fault that connects up with the Magadi Basin. But we're seeing that the focal mechanisms and the earthquakes are along projections of the border faults, and they make sense then, the slip planes make sense with projections of these faults to depth. They're occurring at the base of the border fault and then potentially an intrusive zone into the center part of the rift. And this is a tomographic section across the same area with the earthquakes plotted on top. They're in the zones in between the low velocity areas. These are the volcanic edifices of Gelai, this is the northern end of Gelai, and the sedimentary basin here, and this is what we interpret as a magma chamber with the top only at about 15 kilometers depth. So still deep within, or relatively deep within the crust. And so the implication is, in this case, that the seismicity is associated with fluids within the crust and effectively hydraulic fracture. And I'm not going to talk about this one, and that was the Tanganyika, but only just to quickly tell you that, again, we see even deeper, and they're right along projections of the border faults they're well constrained. But here, what the gas chemistry is showing us is these are the hot springs along that same fault system. These are CO2 fluxes, and these are some of the largest CO2 flux values estimated in continental regions here. So here's the major border fault system. This is a conjugate fault system on the opposite side. This is roughly this profile through here. We see very large values, nil values across the basin, and along these fault systems then we're seeing active CO2 degassing to the surface. And the chemistry of the CO2 then requires that it's mantle source. There's a very, very small percentage of biogenic contribution. And so this is CO2 that's coming from degassed magmas and percolating then upward along the fault systems. And the flux then, if we take the whole main Ethiopian rift and eastern rift system and take the area of those and the fault systems, that would contribute about 71 megatons per year, and that's about 11% of the global budget, and comparable to the CO2 flux out of mid-ocean ridges, just from the East African rift alone. And remember that these rifts are very wide. They may be 60, 70 kilometers wide, whereas a mid-ocean ridge might be 10 or 15 kilometers wide. So the active fault zone, so the flux across these areas then may be much larger. And so our working model is that microseisms and the saline fluids maintain permeable pathways for the volatiles and the high pore pressures from CO2. And this is the CO2 flux compared to volcanic arcs worldwide. These are volcanoes. So most people think about CO2 fluxes coming from volcanoes near Congo, Mount Etna. But here's the Magadi Natron Basin away from volcanoes. So at least all of the observations here are more than 20 kilometers away and well away from the carbonatitic volcano Doña Langai. So we're seeing very large values that are comparable to volcanoes coming up fault systems. And then this would be then the new flux estimate then compared to plume passive degassing, diffuse emissions, and arc volcanism, and mid-ocean ridges. So it's going back to those first diagrams, the flux of CO2 out of rift zones is non-trivial and needs to be included in global budgets and part of the carbon cycle. It's not the first time that folks have said this. Lindenfeld et al. and Gerhard Grumker and his colleagues in Germany looked at it, found mantle earthquakes, small magnitude mantle earthquakes, and then crustal earthquakes that migrated upward, swarms of crustal earthquakes, and interpreted them as evidence for CO2 percolation degassing. And again, this is an area with some very large, small volume carbonatitic volcanoes that are associated not with unusual carbon-rich layers, but instead just trapping the CO2 in the unusual lavas. So if we look at these magma fluxes, our magma production rates from the, whatever sparse seismic data and the gas flux data agree to about 20%, which shocked Toby Fisher and I. And we don't want to dwell on that because these are really crude. But when I take volumetric estimates for the magma production rates per million years in the Eastern Rift and compare them to those for the Aleutians. So we came up with 5 to 90 cubic kilometers per kilometer along the length of the rift per million years. That is on the order or spans what Steve Holbrook had predicted for the Aleutians. So these processes then are the magma production rates in East Africa, maybe on the high side for rift zones, but they're important in contributing new material and new mass flux then to the plates, and they're an important contribution to the global CO2 cycle as well. When it comes back to this idea about fault zones, it was with great eagerness I jumped into this over the past year or so and came up with the overwhelming response that I don't know, and I know less than I did when I started, because at the lower crustal levels that we're talking about 15 kilometers or deeper, CO2 is a fluid, it's a supercritical fluid, and there's not an experiment to tell us even how the rocks will respond, nor can we use some of the geochemical models like melts or to consider this problem, because gas-rich basaltic systems then are quite unusual as well and require new theory to be able to move forward these ideas. But our speculation is that the high pore pressures from these CO2 fluid phases are potentially an explanation for these very unusual lower crustal earthquakes and potentially mantle earthquakes throughout the East African Rift. And it's an evidence of this pervasive process of mantle metasomatism that may be weakening the plate and enabling rifting in what was originally strong, thick, cold cratonic lithosphere. So yeah, this is where I get to the big wrap-up part, and I don't know, this is back to my sad jokes as well. Peter Jackson might have said this was apt volcano to put in the background, Mount Doom. But I think fluxes in comparison with volcanic arcs have shown that rift zones are an important contribution. And it's where surface processes and orographic relief, after talking to Nikki White yesterday, I threatened to show this, and I'm now going to as well. As Nikki and others were, and many students, this is Rundle at Roberts, White, and Richardson, looked at relief in Africa and the creation of relief by looking at stream river profiles throughout the continent, or well-constrained river profiles. But we're commenting that the plates respond quite quickly, and topography is created more rapidly than I think had been previously proposed. And in part, that happens, as Nikki said, the mantle's like a waterbed. I think that might be a bit of an overstatement, but we see compelling evidence that there are fluids, there's hydrous fluids rising to the base of the plate, and they're magmatic fluids, and that they can help explain these shorter time scales of the creation of and removal of topography in tectonically active areas. Taking these basaltic melt volumes that we have, I just take some more. I wanted, as a wrap up, this is Kathy Whaler's, or DeSissa et al. Work using MT, and this is showing receiver functions superposed. You see the very small amplitudes in this area within the magma chamber near the base of the crust, the strong attenuation caused by these fluids. But they estimate 13% melt in the magma chambers, perhaps. That's and compared to 4 to 20% melt in a mid-Atlantic ridge. The top of the magma chamber is somewhere on the order, somewhere perhaps at 5 near the ridge, and goes down towards the base of the crust. Folks in volcanic arcs, this is work in press by Pritchard and Gregg, comparing this massive body in the Andes, the Altiplano Puno volcanic complex, and MT. You know, this is comparison. MT, seismic, and gravity don't give the same exact dimensions, but very large percentages of silicic melts as well in this area. So we're finding that magmatism is an important part of also the process that creates topography in the orographic relief in many of these tectonically active areas. And finally, just last diagram. Rifts in the return flux of mantle at subduction zones. This is from Iberian margin. This is from Rheologically et al. Work looking at mantle velocities. And this is the zone of serpentinized uppermost mantle, where fluids presumably fluids entered into the mantle through these rift normal fault systems in this sketch down through here. So the serpentinized zone, there are fluids in here, but then we have large areas and large volumes of material. And this diagram here on the right-hand side is water volume per unit length versus displacement. So the largest displacement faults will then allow a larger percentage of water. So as subduction zone processes or passive margins then enter into subduction zones, the introduction of these fluids then may cause pulsing or rate changes then in processes, in the tectonic processes, and that should be also then considered. So rift zone faults not only serve as conduits up and out, but also as conduits back down. So I'll leave you with the summary and say thank you very much for your time, and also to emphasize as well that I didn't say much about it, but the new work also points out and highlights that the hazards of the need to reevaluate hazards throughout the East African rift and rift zones in general. There's a much larger magma flux than had been previously thought. There's a much larger CO2 flux in the extreme case here of, this is Nyiragongo volcano and Nyamuragira volcano, both of which have lava lakes at this moment in time. And this is this beautiful Lake Kivu that's saturated in CO2 and methane. Methane's being extracted to generate energy successfully at this moment in time, hopefully without changing the ecosystem within the lake and providing clean energy to Rwanda. But I think you can see that 2.5 million people living right down here and in this area, you know, we hope we get it right. But I think CO2 flux, magma flux are important and have been underappreciated. So thank you.
Thank you very much indeed, Cynthia, for this tour, and now time for questions.
We have a lot of water in the mantle, and the rifting, as you said, we have a lot of relief
or the numbers are so crude because we have point measurements. We do things like extrapolate to large areas, and then to keep going and make even more extrapolations. I think I drew the line at where that was, but I guess my point in response to your question is that this kind of high flux may only be relevant for a short period of time. So if we have a metasomatized mantle lithosphere, as that mantle lithosphere then heats and stretches and thins, we'll have a decrease, we necessarily have a decrease in the flux of volatiles. And so that it'll be pulsing and variable spatially over time, depending if we have propagation. And the same with that subduction. It's a passive margin, it would be like a flash in time as well as it then enters the subduction zone. So I guess I would say more that there should be times where there might be imbalances and balance back. But I probably won't be living to be able to test some of these over long periods of time needed to be able to do that. So it's probably safe for me to make these speculations.
So a related question. Actually, I was really intrigued by your sort of relationship between the volatiles and the fluids and the seismicity we see. And obviously we see seismicity at quite a lot of different scales, but we see volatile release at quite a lot of different scales. I was wondering if you could use the seismicity in any way to predict where we might see the larger gas fluxes. Just for example, the measurements from that basin, I'm going to pronounce it wrong, but the Rheologically study looks quite different to what we see further north in the main Ethiopian rift. And I wondered if there was anything to draw out in terms of the relationship between those two phenomena.
Okay, what I would say at this point in the rift, so another 50 kilometers, the next segment north from the Magadi Basin, you enter into the zone where there are central and fractionated volcanoes. So we have silicic systems that are much shallower in the crust, and these really productive geothermal systems that are providing energy to, over 50% of the energy to Kenya, and Ethiopia will soon, I hope, be in the same category. But those are absent to the south. So my suspicion is that once the magma reaches to shallower levels, you develop a much more focused system. And I would imagine that the volcanoes are most likely the loci of the gas flux with the surrounding faults there. But so we probably overestimated the flux, but we excluded volcanoes. So, in a way, the numbers may be about right if you put the volcanoes back in. We took faults only and then whatever. But it's not knowing that part and the evolutionary part of it that becomes, or having a larger swath of the rift image, and perhaps your experiment, I'm looking forward to the rift fault experiment in Ethiopia to provide that bigger swath and larger comparative area.
Next question.
So, I've thought quite a lot about rifting, and also about cratering. What I want to know is your thoughts on why rifts form near old orogenic belts. Is it perhaps because you've got metasomatized mantle lithosphere in the mobile belts, or because you've got thinner lithosphere in which you can pond plume material, or is it a bit of both, or something else?
I can't think, I've been thinking about this for a long time, because which one is a bit of a chicken and egg too, is which one's more important. But if you look, how would you tell the difference? Understanding the timing of the metasomatism in the rocks, having a nice xenolith suite to be able to say. So I think in Ethiopia, the metasomatic events were Pan-African, and so the role there is quite important. But in other areas, it looks like it's young metasomatism. So until we have a better idea, I'm not sure that we can address the problem. So I turn it back to the geochemists and provoke the question is when when were the fluids added to the mantle part of the lithosphere? Are they associated with the present day plume that would say that it was the edge of the cratine influence versus the older part that had to do with the Pan-African subduction collision processes as well? Maybe someone knows. Does anybody know the timing?
nice, but you ended on hazard. And I think a really interesting thing that you might see in Craig McGee's post tomorrow is looking at cylinder placement in the sediments down Kill Basin. So one of the things we maybe don't always appreciate, which accentuates the extent to which hazard assessment is really important in East Africa, is that you can get cylinder placement, as I understand it, cardinal horizons without any surface deformation. It's almost completely, the replacement is without surface deformation that might be recorded by INSEL. So I think you're right about hazard assessment.
Yeah, well, and sills, thin sill intrusion, if it's deeper, if the land surface isn't perfect, perfectly unvegetated, it isn't ideal conditions, if it's much deeper than 10 kilometers, it'd be almost impossible to detect anyway. I mean, even if it was within rock, because of that damping of the signal of this long, thin sheet as well. So that's the huge question. We know that it must be mostly long, thin sheets because of the heat. When you do the heat budget calculations, and we can't just do it all in these thin vertical sheets. So, yeah.
Okay. No, I think this stops here. We would like to thank you again very, very much for your talk and efforts to prepare everything for us.
Thank you.